3, 2, 1. Okay, so calculus is all about finding numbers between two other numbers on a curve or a line. And the closer you get to two consecutive numbers, the more likely you're going to get a fairly precise value of the slope or whatever it is you're trying to find. And so this chapter really is all about laying down the ground rules for what we're talking about here. So this particular point in the chapter here, there's a number of rules that they're going to establish. It's going to sound pretty basic, but they're important in how we're going to do the concepts from here on in. The first one talks about continuity versus discontinuity. And your book uses these three graphs as examples here of discontinuous functions. Now this is in an open interval because your beginning points and ending points of these curves are not totally defined. They don't include those particular numbers A and B. So this is called an open interval. If in that open interval there is not a distinct C, then this f sub c is not defined, and therefore this is not considered continuous. This is discontinuous. Over here, when we get to C, we get a value for this part right here, but at that same C you have an option or a value that's not contained in part of this interval. So the function of x here, where x approaches C, is not the same. Therefore, we don't consider this continuous. It stops and then starts over someplace else. So you have two different starting and stopping points in these intervals. So that makes this discontinuous as well. And over here, this is very similar to this right here, except, oh look, this is a point right here. Well, we had this in our one of our first assignments when we were asked about that, and this, because of this being not part of the curve, this kind of stops and then jumps down here and then starts again and goes back up there. That's not continuous either. And this is showing that f of x does not equal f of c, where f of x would be this right here and f of c would be, I'm sorry, f of x is this right here and f of c is this particular point right there. So since they are not allowing the same number at c, then this is not considered continuous. Okay? To be continuous, three conditions must all exist. That your function in terms of c has to be defined. It's got to be a solid point at that particular c, not a solid and open or an open. It's got to be completely defined. The limit of f of x as x approaches c exists, and the limit of f of x must equal the f of c as x approaches c here. So those three all have to be true in order for the function to be considered continuous. And this is called the continuity theorem of open intervals. And if the function is going to be continuous, it is continuous on every point. And that's the key there, is every point included in the function. A function that is continuous on a real line, and this is open because we use parentheses here. This tells us that we're dealing with an open function, and particularly since you have negative infinity and positive infinity, which is not a definite point, so this has to be considered an open interval. The function that's continuous on a real line with those open points is everywhere continuous in order to be considered valid as in continuity. So in an open interval, I, if an open interval I contains a real number c and the function is not continuous at c, then the function has a discontinuity at c. Okay, so if the point that you pick, or if there's any point that you pick between the two ends, with a and b, or negative infinity, positive infinity, whatever your starting and ending points are that are not included in that, and it's the same for closed intervals, which instead of using parentheses we use brackets. It's the same idea. There are two categories of discontinuity, removable and not removable. A function is removable if it can be redefined, and we're going to take a look at some examples of how we can redefine a function, and we've kind of done it already, so this is nothing really new, it's just now we're putting words to this. A couple other things too that we need to identify as it gets thrown at us is this concept of C negative and C positive. And so if we talk about the existence of a limit, we have to be able to approach the limit from two different directions on a line or curve that we're dealing with. So if f is a function and c and l are real numbers, then the limit of f of x as x approaches c is l. So we've been doing that. And I have here IFF. This means if and only if. This is a shorthand form that you might want to learn because in your calc class in college, this is going to crop up a lot, and rather write all that out, put IFF. And most math students develop that shorthand form of if and only if. Then the limit of f of x as x approaches c is L if and only if the function of x as x approaches c from the negative side, meaning you start on the left of the c approaching c, if that function limit is L, and the limit of f of x as x approaches c from the right hand side, so you start on this side of the curve and approach to it, and you get the same value. If those two are both true, then L is definitely your limit. And again, we're going to see examples of that as we go through this. And the last one, again, is almost part of the Mr. Obvious toolbox. But again, it needs to be stated clearly because many arguments are going to have to be based upon this concept. And that is the intermediate value theorem. And the name pretty much says it all. An intermediate value is somewhere in the middle between the two endpoints. And this now deals with closed intervals, which is not a whole lot different than open, except now you're definitely starting at A and ending in B, and includes both A and B in your graph. If f is continuous on the closed interval a, b, and k is any number between f of a and f of b, in other words, if you take these x values right here and put it into your function, you're going to get a y value. That y value is called f of a and f of b. So a has f of a and b has f of b, so you have those 2 points. Then there is at least one number c in the closed interval ab, such that f of c equals k. And what they're saying there is that at x equals c, you're going to get a y value that they're going to call k. So you got to try and keep all these variables that they're throwing at you in mind, what they really mean. If you really understand that, you see that, well, yeah, this makes total sense. You know why? They're just giving letters and definitions to things that are pretty much obvious, but not obvious to you because you never really had to confront them. But once you get a chance to confront them, you go, yeah, okay, this makes sense. So if you're not sure what this all means just yet, give it some time. It will. So if you go to page 78 in your book, the first section that deals with problems about functions and limits, the first one is a straight line graph. It doesn't say if it goes on and on. There's no point on the end, so I'm going to say this is probably an open interval, so that just continues on to positive infinity over here, negative infinity over here. And in order for this to be a continuous function, these three things must be true. The limit of x has to be a certain value, and the value here, as it says x approaches from the positive side, so we go to the positive part of the graph and come over here, and you see it approaches 3 at, or 1 rather, as x equals 3, so the limit here is 1. We do the same thing from the negative side of this point right here, so we come over here, and we see that we end up, there's no disjointedness, no discontinuity as it approaches, just like there was none over here, so it will stop here without any interruption. And at the point of 3, 1, so the value of f of x is 1, which is your y value, and that is 1. And if these two are both true and equal to the same thing, then we can say definitively that the limit of the entire function is 1 as x approaches 3, because you get the same thing going in either direction. That's what all that means. Okay, so this is a continuous function based upon that. Over here, however, is a different story. If we take a look at the limit of f of x going from the positive side from 4, so that means we're coming all the way out here and coming over here, and the limit is at this point right here, and this value here is, for 4, is positive 2. So that's where that 2 comes from. Now for the next one, as you go along this function here, on the negative side of 4, you're going in this direction, and it gets to this open point right here, because this is already established as C right here. This is C for sure, this is C open right here. But as we go there, the limit for that is negative 2, and not positive 2 like it was up here. So we put negative 2 there. And since these two do not equal each other, then the limit of f of x as x approaches 4 does not exist. This is considered a discontinuous function. And you can see the graph that it's not continuous. You can see the graph here that it is continuous, but this is how you can prove it using the definitions that we have given you. Okay? So let's take a look at some other problems.